Right, hello everyone. Um, Unfortunately, I am not feeling well at all today. But the good news, bad news, depending on how you perceive it, is I did teach this last semester, the spring semester when the whole virus thing started. So I do have recordings for like the last half of this course. So instead of us having to just take this as a loss, what I'm going to do is I'm just going to play that video starting at the material, so you don't have to go through all the due dates and stuff that would be non-existent for us. During the playing of that video, for some reason I mention any due dates that say, April or May. Obviously those are not correct. So these are the due dates for the test 3 and the final exam, everything about that. So we'll talk about this for a minute. After that, I'm just going to hit play. I'll explain something in a minute about that, because I'll have to skip at some point, but let's do this first. So test 3, which we were already well aware was going to be on chapter 7 and 11. For chapter 7, only 4 sections, 1, 2, 5, and 6. And then for chapter 11, 3 sections. That will be Wednesday the 9th and Thursday the 10th. It will be just like the first 2 tests. It'll be in my math lab. You'll have 2 hours, 20 questions. You'll have to submit your work in Canvas within 15 minutes. Please don't forget to do that. The one thing that is new is that you are allowed a calculator, and you will want to use a calculator for some things, as we've seen with those vector calculations, as we've seen for some of those law of sines and cosines calculations. We really needed a calculator. And please make sure that you read the instructions carefully and round as necessary, because if you round incorrectly, you're not going to get credit for it. You can go back and email me and say, hey, Mr. Beckner, check out question 7. It said to round in the nearest 10th, but I rounded to the nearest 100th. And then I'll give you some partial credit for that, but I won't give you full credit. It would be most credit, but not full credit. But yeah, per usual, communication with me is the key. So that's test 3. And then unfortunately, which usually happens in this course, the final exam is going to be the next class period, quote, but we won't actually have class that day, as you can see. So the final, and this is different in a couple of ways, it will only be one day, and it's only going to be one day because that's how finals work, and we are not going to have class on the day of the final. So right now, this is our next to last meeting. We will meet on Wednesday the 9th, and then that's it. There will be no more classes, no more recordings. So next week, the 14th, you take your final, the 16th, you have off. So the final will be 28 questions, 2.5 hours, so I'll give you just a little bit more time. It'll be in my math lab, and it will cover up to section 10.2. Now, I'm not saying 10 chapters with material. I'm saying the chapters that we've covered, which were chapters 5, 6, 7, 11, and then 10 will be the last thing we start, and that'll be the day. But we'll only complete 10.1 and 10.2 this week. I might get a little bit into 10.3, just kind of the bare bones idea of it, but we won't really get into any examples, so I'm not going to test on it. And the good thing about 10.3 is it's on graphing parabolas. You've already graphed parabolas before, but you did it in a completely different way. So this chapter 10, we approach things from a more geometric idea, and I'll let the video give the details so I don't say anything wrong. But the final, you'll be allowed your calculator, no notes or books per usual. I'll have the review available soon. I will say before class on Wednesday. Hopefully I'll have it up tomorrow. If I didn't already put it up earlier, like I said, I do not feel good at all. Same as always, show your work, submit in Canvas within 15 minutes. Yeah, that'll be it. All right, so I'm gonna play this video right here, again from a previous semester. You can see it was from April. I'm going to start at this 17-minute mark, and when we get to about the 50-minute mark, I'm going to skip about 5 minutes. So I'm going to go ahead and warn you, I made a pretty bad error in this video that I remembered, because I take notes on all my videos. And it's just a matter of all the work up to it, up to the graph was good, and then I wasn't paying attention, and I swapped 2 numbers and I made a bad graph. I'm going to skip over all of that, and I'll come back in to right where you're going to hear me be just a teeny bit frustrated for losing 5 minutes worth of time. And then we'll get to the graph. So the graph will look a little sloppier because I was rushing it, but it will still be a good enough representation, and then all the rest of the information will be accurate. So again, I will be skipping over all of the wrong part, which is about 5 minutes worth. Yeah, so let's go ahead and get it. Well, I guess I don't need to remove that. So chapter 10, the parts we study at least, I think there might be a 10.4 that doesn't have to deal with this. The chapter 10, the 3 sections that we study are on what we call conic sections. Now, what I usually do at the beginning of this class is I would go to YouTube and I would pull up a video to help us get a visual aid for conic sections. However, I am going to be posting this on YouTube and I'm going to be recording someone else's content. I'm kind of scared that there's copyright law that I might be infringing, and I don't really want to play with that. So I'm going to suggest that after class, you pull up YouTube and just type in conic sections, maybe demonstration. There might be an extra word to type, conic sections or conic sections demonstration or conic sections basic explanation, something like that. And you will get a nice 3-dimensional video. One of the first 2 or 3 options, the one I always like has a British voice over it, I believe. Or maybe it was a computer voice, a British computer voice, something like that. So I'm just going to give you a very terrible drawing to kind of show you what it goes through instead, so that I don't get sued, because everybody wants that, right? I mean, I'm a teacher. It's not like they're going to have any money to take. Ha 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 ha. All right. So here is a 2-sided cone. So this is a 3-dimensional shape. This is a cone on top of a cone where they're meeting at a point. So this right here is a singular point. That's the top of the bottom cone and the bottom of the top cone. Imagine you just took 2 ice cream cones, the round, the actual cylindrical cone style, the waffle cone style, that is to say. And you just took their 2 bottom tips and you touched them, so that, you know, if you had ice cream inside of the bottom one, you'd hope that you really jammed it in there so it doesn't fall out and upset your 2-year-old or 3-year-old or whatever. So this is the image that we start with to describe conic sections. And then what we do is we cut this thing with a plane. So we have a 2-dimensional flat plane. I don't want to do it that way. And this is really difficult for me to do. And if you were to take this 2D plane versus this 3D cone, if you take that plane and you just kind of cut it horizontally. So in other words, this dotted shape right here, if you were to take your plane, let's say this was a piece of paper and you could just magically slide it through this cone, then the cross section of the cone on top of the plane would be that circle right there. So this dotted shape right here, that's a circle. That is one of the several images that you can get by doing this. Now this is if we have that 2D plane completely horizontal, completely parallel to the base of the cone. There is another way that you can do this. So I need to draw this image again, and I'm not going to do all of these because I know there's one of them I can't even draw. So the dotted portion is saying that's hidden, it's behind it. We can't technically see that backside of it. I could have drawn that a little more symmetrical, but it is what it is. If you were to take this thing and you were to slice it vertically instead, actually the back one is dotted. And I shouldn't have done it that way. I'm trying to demonstrate that I'm slicing it down the side, across the top. The image that you get here, so I'm going to redraw that one. So again, the same demonstration, just from a different angle. So now we're looking at it from the side view. So this is kind of a left view. This will be a side view. So let's take it and do it this way. No. Got it. And that's solid. I can make that a little straighter. I told you I didn't really want to have to draw this. But anyways, the shape that you'd have inside here, from where it's intersecting, end up looking like these. They end up looking like parabolas, and that's exactly what they are. So if you slice it horizontally, you get a circle. If you slice it vertically, you get a parabola. If you were to instead, and I'm not even going to try and draw, like I said, this last one appropriately. The video is much better. But if you slice this thing at an angle, the shape that you get inside would be a hyperbola. And I'm not gonna, like I said, you really need to please go and just pull up a video on Conic Sections demonstrating this. It's gonna be able to do a lot better than I can with a crappy drawing tablet, lack of artistic ability. And just, yeah, so again, please do that. I will say that a hyperbola is going to look very similar to a parabola. So parabolas, you only end up with one or the other when you actually draw them to be functions. That's what we've always seen in the past, but we don't always have to have that necessarily in math. You can have both top and bottom, but we generally don't. The hyperbolas, you always have the top and the bottom. So we know what our circles look like. That's not circular. And then the last one I didn't draw was an ellipse. So we have our circle. And actually, that's not a hyperbola. This is supposed to be the ellipse. Sorry, I'm getting so focused. This is not a hyperbola. This is an ellipse. Obviously. The hyperbola is when you go through at a less angle. It's still if you do it at an angle, but it's if you go at a smaller vertical angle. So if I were to slice it like this, that's how you get the hyperbolas. This is an ellipse. So what's an ellipse? Well, this is a circle. An ellipse is just a circle that's been stretched out. A parabola, we all know that shape. But then a hyperbola kind of looks similar, but they're a little wider generally. And they do have a top and a bottom. Hyperbolas are not necessarily functions. So hyperbola kind of sounds like the word hyperbole, which is to exaggerate, and they honestly have nothing to do with each other. Just like a parabole has nothing to do with a parabola. Gotta love math people, right? But these are the four shapes that come out of your conic section. So I demonstrated the circle, the ellipse, the parabola. I did not demonstrate the hyperbola. I meant to show you what the hyperbola should look like, but my bad drawing, and I didn't even think about it, ended up giving the cutout for an ellipse. So I can actually do this one. Just looks like a wider circle. And I didn't draw that further enough over. It should be like that. There we go. Should be touching the edge of it. There we go. There's our ellipse. Not a hyperbola because we did not slice it the correct way. I said the reason if you slice it vertically, you would go through, not vertically, more vertically, you'd go through two sections of the cone, which is why you end up with the two images.
So am I ever going to have you testing or questions on any of this stuff? Absolutely not. This is just a demonstration of where these shapes come from. Now, you've dealt with circles before in math classes. You've definitely dealt with them in Math 161. You've dealt with parabolas in math classes. You definitely dealt with them in Math 161. You've probably seen ellipses, but you may not have seen their equations. And I would actually be surprised if more than 10 or 15% of you have dealt with hyperbolas before, unless you've actually gone through this course or gone through calculus. Hyperbolas are something that, what's the phrase I want to use? I don't know how PC that phrase is. It's not rude or anything. I just don't know if I want to say it on recording. It'd be fine in class, but so you don't see these as much in an introductory calculus class, but what's fascinating is they become extremely relevant in higher calculus and things like partial differential equations and other side topics, numerical analysis. And in fact, you can actually combine the idea of a hyperbola with trigonometric functions, and you get a hyperbolic sine and a hyperbolic cosine and a hyperbolic tangent. And they behave similar, but quite different. So they have features of a hyperbola, they have features of a sine, but they don't have every feature of both of those classifications. That tends to happen when you mix and match things. So this is just that bare introduction showing you where these shapes come from. It's all based on how you would slice this three-dimensional image with a two-dimensional image. So let's get into the first official section, 10.1, the ellipse. Okay, so an ellipse, is the set of all points in a plane whose sum of the distances to the two fixed points is constant. And I'm going to all caps that word. An ellipse, we have to think about this for a second. This kind of sounds weird, right? An ellipse is the set of all points in a plane, so that means a two-dimensional shape, whose sum of the distances to the two fixed points is a constant. To two fixed points. There shouldn't be a the there. Sorry about that. I mean, they are specific, the two fixed points. But it doesn't make sense until we explain what they are. So an ellipse is a set of all points in a plane whose sum of the distance to two fixed points is constant. So let's draw an ellipse, and they don't have to be like this. They don't have to be wider, they can be taller, and we will see instances of both. So an ellipse, the set of all points in a plane, so this kind of circular-ish but elongated shape, whose sum of the distances to two fixed points is constant. So we got a fixed point, maybe about here, and a fixed point maybe about here. I'm going to label them F1 and F2 for now. I call them Fs for the first letter of the word they're associated with. And then we have any point on the circle P. So it doesn't have to be this point right here. It could be over here on the far right. It could be the very bottom center. It could be the top left-ish area. This P represents every single point on the ellipse. So we have the distance from this point to F1. That was a terrible looking line. Let me start from here and go up. I tend to be better going left to right. So this would be D1, the distance to F1. This point right here, this distance right here from P to F2, let's call that D2. No matter where you are on the ellipse, D1 plus D2 is constant. It never changes. So if you're on this point, let's say D1 was 7 and D2 is 3. That would add to 10. That means if you were on this point over here on the far right, then if you don't know the distances, you can at least say that their sum is 10. So maybe you know the distance from F2 to the right is 2. That means the distance from F1 to the right would have to be 8 because 2 plus 8 is 10. Or maybe you're here, right dead center. The distance from F1 to the center would have to be 5. The distance from that bottom center point to F2 would have to be 5 in order to add to 10, because it'd have to be symmetrical. That is the geometrically built ellipse. You can also build ellipses algebraically, but this chapter is dedicated to the geometric experience. So I said earlier that you should have all studied parabolas previously back in Pre-Calc 1 extensively. You learn about their vertices, you learn about maxes and mins, you learn about how to graph them using their intercepts, their x-intercepts, their y-intercepts. You learn how to put them in 2 different forms. There's actually a third form. It's not in this section, but we'll get to it. And it looks very, very different than what you're probably used to. All right. So now that we know the idea behind an ellipse, let's actually show what the equation for it is. And we're not going to derive the equations in this section. That would be extremely time consuming. So if the major, which we'll call the longer axis, is horizontal, let me underline that. And centered at the origin, the equation is, and we're going to go x squared over a squared plus y squared over b squared equals 1. Then there's a little side equation that c squared is equal to a squared minus b squared. So I'm going to have some typing after this to explain what the a, b, and c are. A is the distance to the vertex on the major axis. B is the distance to the edge along the minor axis. That's a lowercase a, not a capital A. Thank you, Word. So, what are the A and the B? Let me get a different color to represent up here. A is the distance to the vertex on the major axis. The vertex is the far left and right points in the way we've drawn this up here. These are the vertices. That's the plural of vertex. So this would be V2 and V1, V for vertex. Now, the top and the bottom, we don't really like to call those vertices. That's why I said to the distance to the edge along the minor axis. So in this image, the major axis is horizontal. And the minor axis is vertical. Major, longer, minor, smaller. Pretty easy to remember. So again, A is the distance to the vertex on the major axis. So what color do we want? Let's go with orange. From here, from the center to the vertex, that distance is A. That length is A. From the center to the top or bottom, that distance is B. And again, it works if you draw that down or left. That would be A, going left from the center. This would be B, going down from the center. But what exactly is C? C, lowercase c, thank you, Word, is used to locate the foci. That's the plural of focus. Well, guess what? We labeled some points F1 and F2 for a reason earlier. Those are the foci, focus 1, focus 2. So the foci are related to the whole geometric build of this, that those distances are constant. Now, we don't get to see D1 and D2. They're different for every single point. The only time we would ever get to see D1 and D2 is a special case, and I don't want to mention it right now. So if we are centered at the origin, if this point is 0, 0, if we're at the origin, so that we can actually use this equation, then the vertices, since we're going left and right A, they would be, actually I'm going to type it down here. The vertices are at negative A, comma 0, and A, comma 0, because we're going left or right by the A. The foci are at negative C, comma 0, and C, comma 0. Copyright. I feel like that's kind of funny, since I mentioned that earlier. So C is used to locate the foci. That's the distance from the center to the focal point, one of the two focal points. So again, I'm not saying this distance right here is A, this distance right here is C. What color haven't we used? Gray, dark gray. So I'm going to do it on the left side. This distance right here is C. I know it's a lot of things up there all at once. The D1 and the D2 we will never use moving forward. We just use that concept to build an ellipse. So what's really cool is, and if this was like an elementary class, or even I've seen some high school classes do this, what you can do is you can draw an elliptical shape and you can measure a distance from here to here, and you can poke holes in the focal points, and then you can put pins and you take a string and you make the string taut. And then if you have your pen holding down the string, as long as you trace your pen with the string taut, you end up making an ellipse. So again, you just anchor a string down on 2 points, some distance apart from each other. Then you take your pen, you pull it up so that the string is tight, and then you just start rotating it around clockwise or counterclockwise, keeping it tight, and you end up drawing this shape. Because the length of your string, sorry, I blanked for a second, I had rope in my head. The length of your string is constant, you can't change it. So this was all if the major axis is vertical. If the major axis, I'm sorry, horizontal. If the major axis is horizontal, then you have this setup. So A is going to be the larger number. A has to be bigger than B. A has to be bigger than B in this case. But what about if the major axis is vertical instead? That thing I just accidentally said a minute ago. So I'm not going to show every single detail of this same image. I'll show what's important. So here's a vertical ellipse. Let's see, we did green and orange. So we'll do orange for the longer one. So that distance would be A. I'm not that worried about the colors being consistent. This distance would be B. We still have our focal points. Maybe about here, F1, and here, F2. And the distance, come on, give me my other color. From the center to a focal point is C. Now our major axis is vertical. Making the minor axis horizontal. Again, major means the longer. And what I'm trying to demonstrate here is that no matter what, A is supposed to be the longer number. Now, I will admit, in the whole picture, it doesn't matter what you're calling A, B, and C. Those letters are arbitrary. We just like to have them specifically for consistency and setting up examples and everything. But with ellipses, we like A to be associated with the longer side. We like B to be the shorter side. So if, I don't want to do that. If the major axis is vertical, like in this left image, and centered at the origin, the equation is, let's get our black. We're going to have x squared over, now it's b squared, plus y squared over a squared equals 1, where the c squared is the same thing. The only thing that's changed is we swapped the a's and the b's, and honestly, it really doesn't matter what you call them. You could still have this as x squared over a squared plus y squared over b squared, as long as you had the a and the b swapped in the graph. All we are associating is that the bigger number tells you which axis is longer. So if the number under the x squared is bigger, that means that the major axis is horizontal. If the number under the y squared is bigger, that means the major axis is vertical. So the numbers under the x's or the y's are just the square of the distance either in that direction to the edge of the ellipse. So these are your forms for your ellipses that you have to understand and practice. The c squared aspect is also important. I'm only going to highlight it in one of them. It's the same thing in the other. This is extremely similar to a circle. A circle is x squared plus y squared equals r squared when you're centered at the origin. What's the major difference here? Well, you have a horizontal radius and you have a vertical radius, basically. So that's why we have different radii for the x and the y. So it can't just be a single r squared. So basically this divides by that, quote, r squared, but now allows them to be different numbers. So if this was a circle, the a squared and the b squared would be the same. You could multiply both sides by that common denominator, just call the a and the b r. So both bottoms are r squared. You multiply both sides by r squared, and you get the equation of a circle. So we don't really focus on circles in here because all the circle arguments are the same as what you've seen in previous classes. We focus on the ellipse, the hyperbola, and the parabola, but the parabola done quite differently. And we may not get to all of that like we've said, but we're going to do what we can. All right, so let's try this out finally. Example 1. Identify A, B, and C, the important components of the ellipse, and then graph it. And for A, we're going to have x squared over 49 plus y squared over 36, I believe. Yes, equals 1. So we were given the equation for the ellipse. This is not a function. Doesn't matter. Not everything in the world has to be a function. These definitely fail the function test. They fail the vertical line test. They're also not invertible because they're not a function. Even if they were a function, they would fail the horizontal line test. But again, not the point. So we just need to look at this and say, oh, okay, well, the x squared has the bigger number on the bottom, so that means that this thing is going to open up horizontally. Remember, we said the bigger number tells you which one is wider, so that says that the x has a wider range, and it relates to the 49. So you might even want to make just a note up front that this would be a major axis is horizontal case, because the number under x squared is bigger. It has to be wider than taller. So we like to call the a the bigger of the two. So the a squared is the 49. A squared has to be 49 because we're up on this one. If this was vertical, we'd be calling that the b squared, but it's not because 49 is bigger than 36. Well, how do we solve that? You might say take the plus or minus square root, and arguably that's true in an algebra sense, but we're dealing with geometry. You can't have negative lengths of a negative radius for a circle or an ellipse, so we just take a normal square root. So square root of a squared equals the square root of 49. That tells us that A is equal to 7. So the horizontal radius is 7. I'm not saying the horizontal length of the ellipse is 7 because you actually double it. It would be 14 wide. From center to end, it's 7. So that's our A squared. How do we get the B squared? Well, that relates to the number under the Y. So B squared would be the 36. Take the square root of both sides. Again, no plus or minus needed. We've got to skip that a lot in this course, but not always, which tells us that B is equal to 6. So that tells us the vertical length from center to the edge of the ellipse. So it's from the center going left or right, that's a 7 distance. From the center going up or down, that's a distance of 6. Once you have A and B, you can find C using that formula. It's the same formula whether it opens vertically or horizontally. I don't want to say opens vertically, whether it's wider or taller. So C squared is A squared minus B squared. So that's 7 squared minus 6 squared, which is 49 minus 36, which is 13. So we know that C squared is 13, so we take the square root of both sides. Telling us that C is equal to the square root of 13. Those are the A, B, and C. Now, I don't have to give you the equation and ask for the information. I can give you the information and ask for the equation. I can give you the A and B, and then you can build your equation. I could also give you the A and the C, and you can build your equation. Or I can give you the B and the C, and you can build the equation. Because we know how to algebraically rearrange things. I can give you C and A, excuse me, and then you can solve for B. I can give you B and C, and you can solve for A. C is important for the focus. C is important for the focus. A and B are important for drawing the ellipse itself. So again, we got a vertical distance of 7, a horizontal. All right, so that was where the error was starting, so I'm skipping to about 55 minutes in right now. This is current time, Rodney speaking. All right, so shortcut, -7, +7, 6, -6. This should be wider than it is taller because it opens, not opens, that's a bad habit I have of saying it opens horizontally. It's wider than it is taller. That's what it should look like. And then at about 3.5, so if this is 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 2, 3.5, 1, 2, 3.5. So our vertices, we're at 7, 0, and -7, 0. Our foci, we're at square root of 13, 0, and negative square root of 13, 0, where at least the square root of 13 is still 3.6. My bad. My bad. I'm very, very sorry for that. And the best part is it's recorded, so I get to laugh at that later. All right. I'm trying to decide. I actually want to make a memo about that because that was such a more significant mistake. I want to make a memo in the YouTube notes for that. So I'm writing something down to remind myself. Give me a hot second. Okay, so let's just rediscuss this problem to make sure we're all on the same page due to my mistake. We had the x squared over 49, which meant it was going to be wider because 49 is bigger than 36. We did the a's and the b's right. We did the c right. We just drew it vertically on accident because our teacher wasn't paying attention. He was probably doing too many things at once. And then that caused your teacher to mislabel the vertices and foci based on the image. So we erased that. We drew it horizontally like it should be, meaning that the vertices are the left and the right points. The foci should be moving left and right as well. And again, the foci are if you had your string, you anchored it on those points. If the string was the appropriate length, then you made it taut. You could end up drawing the ellipse without even trying. All right, so now that we butchered that, let's try another one, and let's not make mistakes this time. B. And we're going to do x squared over 4 plus y squared over 9 is equal to 1. So this is the format of an ellipse. Now, you know what's funny? If I change this plus to a minus, it's not an ellipse anymore. Just a subtle little detail change like that makes this not an ellipse. It makes it something different that we might get to study if we manage to finish everything in time. I'm probably just going to do kind of a quicker summary next class. I'm going to skip the more complicated problems where we're not centered at the origin. It changes things quite dynamically. And they're fascinating problems. They're very, very useful. But I just want to get the bare essentials in terms of the topic. So the y squared has the bigger number, which means this is going to open vertically, and we'll make sure to draw this one opening vertically. And when I say open vertically, I mean it's taller than it is wider. That open is kind of a misconception. All right, so that means we will call the a squared 9 because this opens, again, that opens. It will be taller than it will be wider, which so we say the major axis is vertical. If a squared is 9, you take the square root of both sides, which tells us a is equal to 3. If b squared is 4, take the square root of both sides. That tells us that b is equal to 2. C squared is the difference of the squares. It kind of feels like Pythagorean, but it's a minus instead of a plus. So we go a squared minus b squared, that's 3 squared minus 2 squared. Some people skip writing it this way because you already know what the squared numbers are, 9 and 4. That's perfectly fine, just 5. So c squared is 5. Take the square root of both. So c is equal to the square root of 5. So we got the A, B, and C. That means we can graph it, we can draw it, we can identify the vertices and the foci. We don't need to label those outer points along the minor axis. We don't really have a special name for them, so that's why they don't get labeled. Yes, you have to plot them to make the ellipse, but you don't give them a name and you don't write them in detail to the side. So we're going to make this, the major axis is vertical. The y squared number is bigger, so we make sure that this ends up taller. 1, 2, 3. 1, 2. 1, 2, 3. 1, 2. So we got the vertices at the top and bottom. That's the 3 and the negative 3. We have the vertices along the minor axis, if you will. Again, no official point, but that's just kind of what I always called them. There we go. And then you connect them in a circular-like shape, but elongated, so it's elliptical. So there's our ellipse. Because it's taller than it is wider, the foci should be along the vertical part. C, we said was square root of 5. Well, the square root of 4 is 2, so it should be pretty close to that. Let's pull up our calculator. I must have closed it. That's all right. So we're going to do 5 square root, 2.2, so about 2 1/4. I'm going to have a really hard time, getting that exactly right. So we just do our best. Not halfway, maybe about here. So that would be one of the foci. And then down 2 1/4 about here, that would be the other foci. So our vertices, that's along the major axis, that's the ones involving the 3 and the -3. Those are 0, 3 and 0, -3. The order of the plus and the minus don't matter, as long as you have 0, The foci are 0, square root of 5 and 0, negative square root of 5. And there we go. No mistakes in this one, I promise. So how do we know it's wider? Because the number under the x squared is bigger. How do we know it's taller? Because the number under the y squared is bigger. We tend to call the a the bigger number. Is it mandatory? No. It just changes. The c squared would then be b squared minus a squared if the b was bigger. In fact, because of the squaring, you could argue it doesn't matter, but it would end up, you might end up having an imaginary number somewhere if you do them backwards. And by might, I mean you definitely would if you're paying attention. All right, I'm not going to be able to fit another one here. So let's do C here. Probably our last example for the day. We did that one, we did that one. Let's go x squared. No. 25x squared plus 16y squared equals 400. I was about to forget my 25. And you go, well, what is this? You said these things had to be x squared over a number squared plus b squared over a number squared equals 1. I don't see any denominators, and that right side is definitely not a 1. This isn't an ellipse. You're crazy, right? Wrong. Well, I mean, I'm crazy, but this is an ellipse. But it doesn't look like it. So we need to rearrange things to make this look like it. Now, the main issue with an ellipse is that the variable terms are positive and on the same side, and that the other side is just a 1. We can make this a 1. Now, you might say, we'll subtract 399 on both sides. Okay, but then you got a minus 399 on the other side, and these numbers in front of the x squared and the y squared, that just doesn't seem to fly. So instead of trying to move this by subtraction, let's try and move it by division. So let's divide both sides, aka all terms, by 400. This is a very common technique. So we'll divide this by 400. We'll divide this by 400. Whatever I do to the left side, I'm doing the right side. And with division, you'd have to do it to all terms. And then the cool thing is all of these fractions are reducible now. 25 and 400 are going to reduce. 400 divided by 25 is 16. So this becomes x squared over 16. That looks a little more familiar. 400 will divide 16 perfectly, and it's 25. 400 divided by 16 is 25. I'll leave you to prove that if you need to see it. So those fractions reduce the tops completely, but the bottoms are 16 and 25 equals, and I hope you know 400 divided by 400 is 1. That was the whole point. Boom, we have the form of an ellipse. And now we can tell whether it's wider or taller. The y squared has the bigger number, so that says that the major axis is vertical. It will be taller than wider. So we'll call the a squared the 25. Taking the square root of both of those, you get a equals 5. I think I can skip showing that work a little bit. The b squared would be the 16. Take the square root of both sides, and you'll get that b is 4. The c squared, that's the difference of the squares of the numbers. So that's the difference of the 25 and the 16. That's the a squared minus the b squared, which is 9. So c squared equals 9. Take the square root, and you get c equals 3. So there's our a, b, and c. We need the a and the b to draw the image. We need the c to locate the foci. Now you can go ahead and identify the vertices and the foci before drawing it, but honestly, as long as you draw it right, I think it's easier to draw it than identify which one's the 0 in those coordinates. But if you draw it wrong, like a teacher may have done earlier, then you would mislabel them. So you do have to be careful. All right, so again, we're taller. The Y has the 5, the X has the 4. I am super paranoid about messing that up now, more so than ever. I'll probably never do it again in my life. So up, 1, 2, 3, 4, 5. Down, 1, 2, 3, 4, 5. Left and right, 4. 1, 2, 3, 4. 1, 2, 3, 4. That's the location of the outer points. And then we go like this. As best as your teacher can do. Good thing is my math lab can draw them perfectly. And there's our shape. But we also need the foci, which the C was 3, so that means we're going up and down 3. Remember, the foci are always located along the major axis. So that's the focal points, the foci. So our vertices, that's the numbers along the major axis. That's the 5s, and we're going up and down, so that's 0, 5, and 0, -5. The foci, still 0, but now it's the 3. And there we go. This is definitely not the extent of the section, but this is probably where I'm going to cut it. I think I would rather give a briefer summary of these 3 sections than do one section in complete, but not the other 2. I just don't feel like that's a good idea because we only have really one more class to lecture. Monday is our last lecture. Can you believe that? And I will be lecturing since the reviews are all digital and everything. So again, on next class, we'll really quickly kind of talk about the hyperbola and the parabola. The test questions on the final exam involving this would be no more difficult than what we've done in the class. If you go to the homework problems, those are going to be above and beyond. I really don't even want to say this. I'm going to exempt Chapter 10 homework from your grade. I don't want to have to remove all of the problems that should really be in there and just give you the 2 or 3 simple ones. So find the simple ones, make sure you understand how to do them, the ones that were like these 3 examples. You don't have to do any of the rest. If you really want to go above and beyond, you can try and study it on your own. But these things don't have to be centered at the origin. You can have a center here, and then your ellipse, if it opens, I keep saying that. Again, bad habit of mine. If it has a major axis that's horizontal, it would look like this. So then these points, the foci and the vertices, I said them backwards, but that was unintentional. The vertices and foci, they're not just the values of A and C. They're going to have shifts involved, which again, just complicates things a little bit. And you can be given equations that are not necessarily in the appropriate format, and you have to complete the square to get them in the appropriate format. So these problems can become much more challenging, but again, in terms of what will be on the final, I'm not going to do any of the complicated ones. They'll be like example 1, A, B, or C for an ellipse, and anything hyperbola or parabola, again, very simple. I'm not going to give you a lot. I mean, I'm thinking 1, maybe 2 questions on the final involving this. Again, I will exempt the homework. I will not include Chapter 10 homework in your grade. You are welcome to try them. Please try them because, again, the simple ones, because it'll help you with the 1 or 2 on the final. But they will not be part of your grade. And no, I will not give you extra credit if you